Hey guys, welcome back. Today we're going to be talking about sedimentary rocks. We've been kind of building up to this topic for a couple of lectures now. When we talked about weathering and the destruction of rocks and how they erode and mass wasting and things like this. We'll be talking about more of that later on in the class as well, because we have to talk about streams and rivers and things like this. And we've talked about how soils formed, but we didn't actually talk about how things like sandstone or mudstones or any of these other things form. So that's going to be the content of today's lecture, sedimentary rocks. These are rocks that settle out and fill in basins, they fill in holes, and there's some amazing things to see in sediments. For example, right up here, we see these people on vacation, and they're hiking around. This is actually a set of sandstone beds. These are called cross beds. You can actually see this is a bedding plane up here, but these are cross beds, and you see they come up there and they end. We'll talk about the formation of those a little bit later on in this section. But over here we see true beds, really nice flat layers. Okay, nice flat layers. This is in the Grand Canyon, one of the most spectacular places in the world to see. A photograph, you can see that's taking up the entire photograph here. It's really difficult to get the entire Grand Canyon into a single photograph. I have not really seen any really good images of it. So any aspiring photographers out there, if you can find something, let me know. But anyways, this kind of gives you the idea. This is kind of the redder section at the lower part of the Grand Canyon, but there's mudstones and limestones and sandstones, and they all mean something about how they formed. It tells us they're like pages of history right here. Okay, down here in the lower left-hand corner, something called a fossiliferous limestone. This one in particular dates to before the time of the dinosaurs, incredible history here. We'll notice that there's fossils. This is an ancient marine animal called a crinoid, and you can see it's actually starting to fall apart and shed these little circles. We're not going to get into paleobiology too much, but just know that it's an important part of geology is the study of paleontology or fossils. All right, and of course with sedimentary rocks comes our own new minerals, right? We've been talking about quartz and feldspar. We're going to see our old familiar quartz and feldspars again, but this is a mineral called a fire opal or opal, and this actually forms in the ocean in a sedimentary basin. So, we're going to see some really cool stuff as we go forward in this lecture, and I hope you really enjoy it. Okay, let's get started. All right, so the importance of sedimentary rocks can never be overstated. They're economically one of the most important resources that the Earth has. And they cover most of the Earth on top of it. If it isn't for the sediments, we really wouldn't have things like rainforests and things like that forming. So what are we talking about here? Sediments and sedimentary rocks cover approximately 75% of Earth. That's a lot of Earth. As a matter of fact, we learned more about sedimentary rocks probably before we ever learned about igneous or metamorphic rocks, which will be in the next lecture, by the way. But they comprise about 5% by volume of the Earth's outer 10 miles. And below 10 miles, they don't comprise any of it. So we're really just talking about the outermost shell of the Earth. Just the outermost shell. And in a way, that's kind of the same thing with igneous rocks, because remember we said that the mantle is largely unmolten, right? It's basically a solid mass, and it's convecting slowly. Well, relatively slowly, about 20 centimeters per year on average. So we're still really talking about the outermost surface. So when we get to metamorphic rocks, we'll be talking about things that comprise most of the Earth. But economically, it's extremely important. They contain evidence of past environments. Sediments, a sandstone, for example, forms in a unique set of environments. But it doesn't form in the bottom of a lake. It turns out sandstones tend to form on coastlines and beaches and near berms and in certain kinds of desert environments called an erg. But mudstones form in ocean basins. So we can use that to put together where the oceans were and where the continental margins were in the past, and not just look at what's going on today. It's kind of neat. Sedimentary rocks are an important resource for coal, oil, and other fossil fuels. And we say this word fossil because coal and oil used to be living organisms, right? They didn't used to be dinosaurs. You'll hear this a lot, that coal and oil are from dinosaurs. They're from ancient life forms, but not necessarily dinosaurs. We'll talk about that by the end of class. And of course, sedimentary rocks are also critical for understanding and exploiting groundwater resources. Okay. So the origins of sedimentary rock are pretty straightforward. We're just basically going to rehash some of the stuff we talked about in previous lectures and just make sure that we have it fresh in our mind. Uh, First off, sedimentary rocks are products of mechanical and chemical weathering. If you haven't seen the mechanical and chemical weathering video yet, you need to go back and find that one and make sure you watch it so that you understand it, as well as the one on soils, of course, as well. So sediments and soluble constituents are typically transported downslope by gravity. So sand is usually made out of quartz. It's a hard part. It gets transported down. But soluble stuff is the things that dissolve by water during the breakdown, the chemical weathering of rocks. The sediments are then deposited and subsequently buried, right? So we can see that this is probably an old set of sandstones and mudstones, and they just keep getting layered and buried on top of one another. So this at one time was the top, but it's been buried by this layer, and so on and so forth, all the way up to the top. As deposition continues, the sediments are lithified into sedimentary rock. This word lithification is important because originally this is just sand and silt and mud that's laid down, and over time it becomes rock through a process called lithification. Lith meaning rock-ified. So it's rockified, think of it that way. And there are three types of sedimentary rocks. There's detrital, so this would be a mudstone, siltstone, even some sandstones all layered up in here. That would be detrital. Or clastic is another word that we like to use in geology. Chemical rocks, and of course organic sedimentary rocks. Down here is an example of both an organic situation as well as a chemical situation. This is the Great Barrier Reef of northeastern Australia. And these are limestones that are being deposited by reefs. So this is actually the reef, and here's a channel that's cutting through the reef and distributing a lot of the water through here that winds up in the limestone itself. Okay, so there's some important things we need to understand. That when we're going forward, we're probably going to have to understand that different sizes and textures aren't going to be important to understanding the environments that create these rocks. So in order to really get our hands on this, we probably should start talking about the different kinds of rocks themselves. So here we have a detrital set of rocks. We're not going to talk about the chemical or the organic ones until a little bit later. But here we see this is a rock made out of larger pieces, big chunks of rock. And notice that the chunks of rock are nice and rounded relative to this other one over here where the chunks that are inside of it are broken. Okay, this rounded one, the one with the big chunks that are rounded, is called a conglomerate. This one over here is called a breccia. The word breccia is an Italian word. It means broken or busted, right? It's all busted up. A lot of us are familiar with this idea of a sandstone, right? We can actually see that there's layers inside of this sandstone. So it was formed in much the same way as we were looking at some of this stuff in the previous slide, which I won't go back to. And then, of course, mudstones and siltstones. These are made out of grains that are smaller than sand. As a matter of fact, you can't even see the grains in siltstone or mudstone. And as a consequence, we just lump silt and clay, so claystone and mudstone, all together into this group called mud. All right, so we have mud, sand, and gravel that make up these different kinds of rocks. The chief constituents of detrital rocks include clay minerals, quartz, feldspars, and micas. Why? Because they're the ones that are most chemically resistant. They're the ones that are most stable in the Goldish reaction series. So be aware of that. Like I said, if you don't recall that, you need to go back to that previous lecture and review that information. Particle size is used to distinguish among the various rock types. So this is what we're doing up here. Conglomerates being big, conglomerate and breccias, sandstones in the middle, mud with the smallest pieces. Okay, so here we can see some really cool photos. And I'm not going to give away, especially this one up here. This is kind of my ace in the hole as we're going forward. But shale is made of silt and clay-sized particles. It forms from the gradual settling of sediments in quiet, non-turbulent environments. We're basically talking about the bottom of lakes or the bottom of the ocean or some place where there's not a lot of action, a lot of energy. And you can get that nice, quiet, non-turbulent environment in those types of situations. Sediments form in thin layers that are called laminae or laminations, right? So this is a very finely laminated rock right here. Same thing over here. It's actually finely laminated, but it's a little bit better lithified. It has something called fissility, meaning the rock can be split into thin layers. So this is a very fissile rock. Here we can actually see the little fissile flakes that are kind of falling down here below. And it crumbles easily and tends to form gentle slopes. And it's by far the most abundant sedimentary rock. It covers basically the bottoms of the oceans, everywhere around the oceans, and it makes up large amounts of the continents, quite frankly, as well. Another cool, so let's look at these things. Here we see a nice fissile shale, basically a mudstone. Over here we actually see another shale, and in it has a fossil. The cool thing about shale and mud is that the grains are so small that fine details can be preserved. It's almost like a grain of sand or a grain of clay or whatever. It's almost like a pixel in a television. If it gets too large, you lose resolution. But in this case, each one of these little grains are so small, they're so microscopic that we actually have really good detail of what this is. And this is in fact a nautiloid. Up here, we see a really cool sequence of rocks. Notice that there's this what we call colluvium or trash rock, stuff falling down over here. But sticking out of it is this shale. And what makes this particularly interesting is this is a picture taken from a formation observed on Mars. What does that imply? It means that Mars at one time had water on its surface, and that this had to have been deposited within a pond of some sort. So that makes this a really cool image. Sandstone, of course, formed from sand-sized particles. Sand-sized stuff is, it's that gritty stuff. You can see it. You can roll it around in your hand. You can use it for all kinds of things around your house, such as sanding and as grit. And it forms in a variety of environments. It forms in mountain belts. It forms on beaches. It forms in large deserts. And it's the second most abundant sedimentary rock. Far and away, quartz is the most abundant mineral. Quartz, of course, is got a hardness of 7 on the most hardness scale. Makes it pretty hard relative to all the other minerals. And it's also very chemically resistant. Remember, on Goldish's reaction series, quartz is very stable. So quartz sandstone is predominantly composed of quartz. So this would be a nice quartz sandstone up here with a penny on it to give you the size of it. And look, you can even see the layers or the laminations within the sandstone itself. Arkose sandstone contains an appreciable quantities of feldspar. And so here we see an arkose down here. The grains are clearly visible, but notice that it's not that nice white color that we see up here on the pure quartz sandstone. This is an arkose, and the pink mineral that's in here is mainly potassium feldspar, orthoclase, K-spar. And notice that they put an Indian head cent on there. Incidentally, this is the exact same thing as this. This is just the predecessor, so the size is exactly the same. And then, of course, the last type is a greywacke, which contains little tiny rock fragments, things of little pieces of clay, little pieces of mudstone, little pieces of basalt, things that are so small that even when they do weather out, they can't form quartz because the crystals themselves already were too small. And so that'll form something called a greywacke. I affectionately refer to greywacke as the ugliest rock on the planet. It's not the prettiest thing in the world to look at. But they are cool rocks, and under microscope they get really, really beautiful to look at. This is actually relatively boring by comparison with this under the microscope. But to the eye, most of us aren't going to make our countertops out of greywacke. We choose to do it out of this, or maybe even out of this. So what does a quartz sandstone look like under a microscope? Well, this is what it looks like. This is what a sedimentary petrologist is somebody who looks at the rock constituents and analyzes it to figure out what conditions created that rock. And so this is what it would look like under a microscope. And we notice a couple of cool things right away. First off, even in the case of a pure quartz sandstone, so these are quartz grains right here. These are quartz grains. These are relatively small in here. These are big ones, small here, big ones here. And we'll notice that there's another mineral in here, and this is almost certainly muscovite. A little bit of muscovite. This actually might be another mineral called zircon, but muscovite here, and up in here, and up in here, and another little piece of muscovite. So these things aren't necessarily pure quartz sandstone, but the fact that muscovite exists in there tells us that it's coming from some place that had muscovite in it, and that's usually some type of igneous pluton, like a granite. Furthermore, muscovite is a pretty stable mineral, and so it tends to kind of go where the quartz goes. It's not as strong as quartz, so you can see it gets squished up. Quartz gets to dominate the rock. The other thing that we get to see is that even on a microscopic level, we'll notice that there's little fine grain laminations here with coarse grain here, fine grain here, and coarse grain here. So even inside the microscopic sizes, we can still see laminations that are quite small. Really cool. But overall, if I was to do an estimate of how much quartz this was, I would say this was probably 98% quartz and maybe 2% muscovite. This is a very, very, very clean quartz sandstone. All right. So we were talking about running water on Mars and what that might look like. So let's look at some more images of running water on Mars. Well, first off, we have a whole bunch of lake sandstones. We have mudstones down here. So this would actually be an old beach on maybe a lake. Here would be the deeper part of the lake at some point. And then, of course, they have the lake outcrop up here to the top. So the lake comes up here. And this is evidence for running water on Mars. The other thing that we have is conglomerate. So conglomerate, notice these big pieces here, and this is actually on Earth, and this is from out of a riverbed. Notice that the sizes, this is a centimeter right here, this is a centimeter right there. The sizes of these gravels are about the same as the gravels here. If Earth is a good example for what happened on Mars, and we notice that this thing is not moving now, it's probable that there was once water on Mars, at least at this location, and almost certainly there was. And another way that we know is looking at, this is another image of actually old ancient sand dunes that existed on Mars. And there's evidence that this sand dune, notice it's not all, it's all blocky, it's breaking apart. That's because groundwater had to flow through that sandstone to make it into the rock that it is. It didn't do it through compression or through anything like that. This is cemented by water going through it and depositing chemicals that locked the entire, or lithified the entire rock together. So we've got evidence of surface water, we've got evidence of running water down here, and we even have evidence of groundwater on Mars. Pretty cool. This is an area of investigation that I think is going to be fruitful at some time in the future, because if there's water on Mars, it makes it much easier for human beings to go to Mars and explore it. All right. So there's some other things that we need to be aware of as we're going through sandstone. We're going to talk about the texture of the grains themselves. With mudstones, we don't really worry about it. They're so small that everything's just kind of uniformly small. There is some variability, but we're not going to get into that for those types of rocks. But for sandstones, we do need to know how to describe these different textures. So the particles in sandstone vary and are classified by their sorting and shape. All right. So sorting is the degree of similarity in a particle size in a sedimentary rock. So I'll just go ahead and down here. You can pause this and read through this if you wish, but I'll just go and work from the diagram. So here we see a very well-sorted image. Notice that all the grains are about the same size. Over here, it's very poorly. We have small grains here with large pieces of quartz or rock stuck in there. And so we notice that as we go across here from this very poorly sorted towards the well-sorted, even into very well-sorted, there's uniformity in size of the grains as we go from right to left. And it's really important to kind of know the difference between something that's very well sorted and very poorly sorted. It turns out very poorly sorted sandstones have difficulty transmitting water through them, which is important for those that are interested in water resources, whereas very well sorted sands are very good, and sandstones are very good at transporting water, and also petroleum for that matter. But those of you that might decide to become engineers, the exact opposite is true. You don't want to necessarily build a building on top of sand or sandstone that has a lot of pore space in it, a lot of open space that water and petroleum and stuff can flow through, because you're inviting trouble to yourself. But over here, notice that wherever there's a big grain, the small grains go and fill in all the little gaps. And so engineers love very poorly sorted soils to build buildings on, and sometimes they actually mix it intentionally like this. It's called engineered fill when they do this. Really, really cool. We're not going to spend a whole lot of time on this, but I do want to bring up one more point, that sorting can help decipher the depositional environment of the rock, and we're going to show how that's done by the end of the lecture. Another cool thing to keep in mind is that not all grains of sand are these nice spheres. In fact, they change from very angular to very rounded. And this is something called the maturity of the sand grains, or the maturity of the sand. So right when it first breaks off the rock, it might look something like this. And by the time it gets tossed around on the beach for maybe 300 or 400 years, it starts to look like this nice round one over here. So this is a well-rounded sandstone. It's also pretty normal for them to have be elongated, not to be pure, perfect spheres. In this case, we see a very angular chunk that's also very elongated. So this is something that you would definitely note if you were studying sedimentary rocks. This would imply that the source is not far away. However, if it's nice and well-rounded, it could actually be very far traveled. Here we've got Conglomerate and Breccia. Well, here's the conglomerate, nice rounded gravel-sized sediments everywhere. There's even, if you can convince yourself, there's actually layers in here going like this. By comparison, these gravel-sized breccias look like this. So this is a breccia. And these are nice angular chunks, and there's a nice fine-grained matrix that's holding it all together. And both types of rocks are very poorly sorted, right? Now, in terms of the environments that these form in, let's go back to this one. This almost certainly formed in some type of river environment or like what we would call an alluvial fan. We'll study alluvial fans again in a few more lectures forward. But notice that this is almost certainly deposited by water. This, on the other hand, is actually created by a fault that has ruptured and busted all the rocks in place. So no water involved in the breaking of the rock, I should say. And these rocks are not really transported very far at all. As a matter of fact, this is probably hosted in the very same rock that the fault is occurring in. So it's not transported at all. Very different environments, but the texture tells you what's going on. All right, chemical sedimentary rocks. I love chemical sedimentary rocks. These are some of the most beautiful rocks on planet Earth, easily. All right. And we've got to start with limestone. So limestone is the most abundant chemical sedimentary rock. It's everywhere. And it's mainly composed of the mineral calcite, which is calcium carbonate, and can form from inorganic and biochemical origins. It can come from both places. So here we see another fossiliferous limestone, really beautiful stuff. These are little pieces of fossil stuck in there. This right over here is a chemical limestone that is actually formed. It's at the bottom of a lake, a dry lake actually, in this case. And of course, here we can see organisms biochemically creating a reef right here. And all of this stuff, except for the white stuff and the structures, not necessarily the animals themselves, which have some coloration to them, that's all calcium carbonate. That's all limestone. So this is a reef forming right now. So if you wanted to study coastal ecosystems, you have to know about how limestone is deposited and created by these creatures. So biochemical limestone originates from the shells of marine organisms. You know, we were talking about reefs, but it also comes from other places as well. Large quantities of marine limestone are formed from corals. We just talked about that. And corals secrete a calcium carbonate skeleton and create reefs. Okay. Coquina, however, is composed of cemented fragments of shell material. So here's a coquina down here. These are a bunch of shell pieces in here. Okay, this is really neat stuff. And chalk is composed of the tests. Tests means very small shells. That's all that means. Chalk is composed of the tests of microscopic marine organisms. So this is chalk right here. This is the same stuff you use to put on a chalkboard. But if you were to look at it under a microscope, you would see these things in here. This is called a coccolithophore, or a coccolith is what they call them. And coccolithophores are these little shields in there, and inside of it is the organism itself. It actually resides in there, and it's kind of the bottom of the food chain kind of thing. But when it dies, these little pieces fall down to the ground, and they make this deposit here. This is an abalone shell right here, and it's also made out of calcite, and there's another mineral in here, a form of calcium carbonate called aragonite. They're polymorphs of one another, but they both exist here on the shell. All right, and of course here's another set of organisms, a special variety of something called a foraminifera that resides down here. But you can also get inorganic limestones to form as well. And sometimes they're confusing. They look a lot like the fossiliferous stuff. But inorganic limestones you can create without any fossils at all. This actually is something that we find occurring all over the world, in the Bahamas, off the coast of Florida, anywhere where we see limestones being deposited, not necessarily in conjunction with a reef, we find these inorganic limestones. So what causes them? So inorganic limestone forms when chemical changes increase the calcium carbonate content of the water until it precipitates. So travertine, for example, is a type of limestone found in caves. It's precipitated when the water in the cave loses carbon dioxide. So when the carbon dioxide leaves, that precipitates the formation of limestone on the caves. Oolitic limestone is composed of small spheroidal grains called ooids. And ooids form as tiny seeds, roll in shallow marine water, supersaturated with calcium carbonate. So this is actually these are not shells. These might have originally just been a little sand grain right here in the middle, and it's just moving back and forth inside of the currents. And as it's moving around and rolling around in the currents, say maybe down here we can assume this is an ocean, the water sloshing back and forth, it's rolling these things around, and as they roll around, they acquire a crust of calcium carbonate, and then a new crust goes on top of that. And so when we look at ancient rocks, like we see this one here, these are in fact ooids, just like these, but they're inside of a rock form. Whereas if you were to go to certain beaches in the Bahamas, this is actually what the sand looks like. Really neat stuff. Another really cool rock, and we already kind of showed you the fire opal at the beginning to kind of get your appetite wet for on Chert. But Chert is basically a microcrystalline quartz that forms from dissolved silica. And that's what gives rise to flint and jasper and agate, are all varieties of Chert, of course. Opal is also a variety of Chert. As a matter of fact, it's the mineral that makes up Chert. So here's an agate right here. Here's an agate arrowhead, or a Chert arrowhead, and it's made. And here's a piece of flint. Flint is well known because you can actually strike it; it'll make sparks. Jasper, certain types of jasper can be polished up into gem quality, but this is also a type of Chert. And of course, petrified wood is also a version of Chert or agate, kind of similar. And basically it's groundwater that has a lot of silicon dioxide, starts flowing through old forests that have been buried in the dirt. And in doing so, it precipitates that silicon dioxide and it preserves the structure of the wood. Really neat. So this is how you form petrified wood. It's actually a sedimentary chemical process. Okay, now in addition to the clastic rocks and the biochemical rocks, we also should talk about evaporites. Evaporites form when you just have a bunch of water, say ocean water, and there's a lot of salts in that, and or even certain kinds of lake water. Those salts, basically, when you evaporate the water away through solar heat, the salt doesn't go anywhere. And so what happens is the salt in the water starts to build up, and it'll start to form crystals as we hit the saturation point of the water. And so here we actually see a couple of really cool examples of evaporites. Down at the bottom one is actually a very common variety of table salt, a mineral we call halite. These are nice large crystals. We would actually grind this up. This is actually so pure you could put it right on your food if you wanted to. These crystals up here are a little different. This is the mineral gypsum, and this is forming in a cave. If you look carefully, these are in fact men climbing around inside of a cave. These are called spelunkers or cave explorers, and this one here is actually climbing up on a single gypsum crystal. These are considered the largest gypsum crystals in the world, and they form in a cave in Mexico. And basically groundwater was bringing in the right kind of calcium and sulfate into the right cavern, and it precipitated these very large crystals. Spectacular. Here's another way that you can get salt to form. You don't necessarily need to have groundwater or an ocean. You can just do it with a dry lake. So in Death Valley, there's a large dry lake here. And what happens is the water comes up out of the ground. It comes in contact with a very hot sun. You know, Death Valley is infamous for its very high temperatures. And it evaporates the water away, but it leaves the salt behind. And so if I was to take a pickaxe and actually dig down here, I don't have to go more than about 4 or 5 inches, and I find water. This is actually a lake that has been completely crusted over with salt. I can walk out across it, of course, but beneath it is a ton of water, and that water is coming up along these cracks and evaporating away and precipitating more salt. And that's what gives rise to these cracks being kind of raised and with the salt coming out. And of course, you can't really talk about sedimentary rocks without talking about organic sedimentary rocks, which are some of the most alluring of all. We've been talking about opals and limestones and sandstones. They're all really beautiful. But the fossils are usually contained best in the organic sedimentary rocks. Here we see an example of how to make coal. Notice that we see coal here, and in it is fossils of ferns. This is almost certainly a sample that was taken from the Appalachians of the United States, back when there were large fern forests depositing large coal beds everywhere that we now exploit for energy purposes. And so how does this form? Well, basically it starts this way. Here we see a swamp. The water is pretty stagnant, so anything that falls in there, it doesn't actually biodegrade very rapidly. As a matter of fact, it's somewhat preserved. And then what happens, it gets buried, it leaves the imprints of the leaves in there, and then if we were to bury it further, we would form this stuff called anthracite coal, which is this really beautiful stuff right here. So the stages are basically this: the accumulation of plant remains, the formation of peat. So peat is a type of organic deposit. You can actually burn it. Formation of lignite and bituminous coal, and then eventually anthracite. Anthracite is the cleanest version of the coal because as you're burying the organic material, the plant remains, over time, it's squeezing out all of the bad stuff that we don't like, all the sulfur and mercury and uranium and all the other stuff that we don't necessarily want in our coal. So the cleanest coal that we have is anthracite. Unfortunately, we don't have a whole lot of anthracite, so much of the world that is powered by coal runs either on anthracite or bituminous coal. This is actually a version of bituminous coal right here. So now we need to talk about how we turn sediments into sedimentary rock. So we have to understand diagenesis and lithification. Diagenesis is simply the chemical, physical, and biological changes that take place after sediments are deposited and buried. And they always occur within the upper few kilometers of Earth's crust. For examples, recrystallization of stable minerals from less stable ones. For example, aragonite to calcite. Aragonite is that unstable polymorph that a lot of abalones and things like that like to make their shells out of because it's a little bit harder. But it's not stable, so when the animal dies, it'll alter over to calcite. Lithification is the process whereby unconsolidated sediments are transformed into sedimentary rocks. So this is a little different, even though it's a part of diagenesis. Compaction, as sediments are buried, the weight of the overlying material compresses the deeper sediments. So you can just simply take a bunch of sand grains, for example, and just crush them together. And by doing that, you can make them all stick together, and they'll turn it into a rock. Another way is cementation. So cementation involves the crystallization of minerals among the individual sediment grains, usually when you have water. So water will be bringing in little bits of silicon dioxide or maybe some limestone, and what it does is it deposits it in the little pore spaces between the grains, and that lithifies the rock in that manner. So just kind of a quick review of the different kinds of rocks we've covered. We should remember that there's detrital sedimentary rocks and chemical and organic sedimentary rocks, and we should be reminded that detrital sedimentary rocks are conglomerate, breccia, sandstone, and of course arkose is important. Siltstone and shale or mudstone, all of these right here. And then of course over here we see limestones, including travertines, so we don't need to worry about that too much. Coquina, which is a broken up rock, or broken up shells that are all formed into a nice rock. Of course, fossiliferous limestone, we've seen several examples of that, and chalk. Quartz can form nice cherts and flints. Gypsum, we haven't talked about it, but those were those large ones that the cave dwellers or the cave explorers were exploring. Halite, which is rock salt, and of course, coal, which is a pretty common mineral for us to deal with on Earth. And fortunately, it's common because it makes our energy bills nice and low. All right, so I was talking about how we can use sedimentary rocks to work out sedimentary environments, to be actually put together old environments, how we know what used to be in a certain location. So this would be one way that we could do it. First off, we can analyze the fact that we got dry lakes over here. Our dry lakes will give us this nice salt crust like what we were showing was happening at Death Valley. If you don't have a dry lake, you'll get just a regular lake environment. You might find a lot of mud and silts and clays and stuff deposited here. But along rivers and river environments and beaches, you'll find a lot of sand. things like this, maybe dunes over here. And in fact, if we look at this little structure right here, you notice it's a blow up. We find beach dunes, we'll find a shore face and surf, and all this stuff is being moved around through offshore sandbars and beach dunes. And the different orientations of the layers in it is what kind of gives away whether it's a dune or it's an offshore bar. Another thing that will typically happen is the material will be deposited offshore in a submarine fan and into deep marine environments. And we know that this is usually fine-grained shales come from doing this. Actually, right here in the submarine fan, we might find a lot of conglomerate and stuff right at the fan itself. But mostly as you go further away, you get muds. And so that gives rise to a diagram that exists in many books, so we have to kind of cover it really quickly, is this idea that you get different facies of sediments that will form relative to, say, a beach. So different sediments often accumulate in adjacent environments. So here we have sandstones that are forming at this position relative to the coastline, but while at the same time this sandstone is being deposited, over here is the shale. And then aside from the shale, further out is the limestone. And they're all the same age. They're all forming at the same time. Okay. So each unit or facies possesses a distinctive set of characteristics reflecting the conditions of a particular environment. Transitions between different facies are typically gradual. And notice how these things zipper back together. That's actually a very gradual occurrence that seems to happen in geology a lot. Okay, other information that sedimentary rocks can give us about the Earth's history can be gleaned or taken from the structures that sediments make when they're forming. So, for example, we see nice sandstones, but you'll notice that there's layers going this direction and this direction, but there's also cross beds or beds that are going in a different direction down this way. And this is almost entirely indicative of the formation of dunes, like a beach dune, or wind-driven stuff. And so in central Utah, this is actually taken from a picture taken in Zion National Park. This is a huge rock unit that extends for many hundreds of miles, actually, all the way from the Grand Canyon all the way up into Utah. This was a very large dune desert at one point, prior to the time of the dinosaurs. Okay, so these layers, or these little cross beds or whatever, are called strata. Strata is an important word. This is where we get the word stratigraphy from. Stratigraphy is the study of rock layers. And most characteristic of sedimentary rocks. We do get rock layering somewhat in igneous rocks, especially in lava flows, but you don't get them the same. You don't get them nice flat rock layers like you see in sediments. And bedding planes are called strata. Each one is a separate strata. So cross-bedding occurs when layers of the sedimentary rocks are inclined. So here we see those nice inclined beds within the layers. And is characteristic of sand dunes, deltas, and some stream deposits. It's actually not very common for stream deposits, but it does happen. So here we see another image of cross-bedding. And this is all sandstone all the way from the top down to the bottom here. And we'll notice that we have nice cross beds going across this whole unit. In this case, the cross beds go all the way down here. And then there's a layer right here and another series of cross beds. And we can actually use this to figure out which way the wind is blowing. The reason why is because the front of the old dune is almost always preserved. So this is the front of the dune. And if the front of the dune is inclined in this direction, it usually means that the wind is blowing from left to right in this image. Kind of neat that we could figure out ancient wind directions if we needed to. All right, so another cool sedimentary structure that we need to be aware of is something called graded bedding. So graded bedding is when you have large grained stuff down here, perhaps conglomerate, and then maybe a zone of sandstone or sand up on top, and then on top you're going to get shale or mud rock of some sort. And so graded beds are basically when it goes from large grain to small grain or vice versa. So graded beds are a unique situation in which the sediments in the strata gradually change from coarse at the top to fine at the bottom, and they're often associated with turbidity currents. So if we see graded bedding like this, that usually means that we're looking at something off the shore and a turbidity current, one of those submarine canyons. And look, here we actually see one in real life. nice gravel sitting right here, and as we go up, it gets finer grained. And it's sitting on top of a layer of fine grained stuff. So down here below it undoubtedly is another turbidity current. We just don't see the bottom of it here. But here we see that transition. So this was probably a pretty violent event that actually deposited this originally. Some other really cool structures. So this is when it really gets neat. Here we see ripple marks that would have formed probably in a shallow lake or possibly a broad river. And we can use this to figure out water direction, but this is clearly ripples that we can see that occur. Down here, these are things called mud cracks. So when water or when clay dries out, it'll form big cracks. Specifically at the bottoms of ancient lakes and when lakes dry out. And so here we actually see the old mud cracks from when the lake dried out. Of course, fossils. Here is a fossil of a tortoise or a turtle, a sea turtle in this case. You can actually see the fins. But this thing here is 55 million years old. And notice that the shell here does not completely cover the tortoise. There's little windows over here. Tortoises over time have gotten more bony material covering their entire shell over time. So this is kind of a cool picture. And of course, we can't talk about sedimentary rocks without talking about oil. If you can't, oil is probably the most important resource on planet Earth aside from water itself. So oil and natural gas are derived from the remains of marine plants and animals. Oil forms in a different kind of environment than coal. Coal forms up on the land in a swampy environment, but oil and natural gas actually form in the open ocean from these little tiny marine animals and plants. Remember those little microorganisms I was showing you earlier, the coccolithophores, for example. And both are composed of various hydrocarbon compounds and found in similar environments. Kind of neat. So in order to get the oil, you need to have something called an oil trap. And an oil trap is a geologic environment that allows significant amounts of oil and gas to accumulate. And so here we can see places where they're taking advantage of oil traps. This is an offshore drilling rig. And then this is, of course, a Saudi Arabian oil field here where they're taking advantage of the oil coming out. And they're actually getting so much natural gas and some extra gases that they don't want that they burn it off. There's two conditions for an oil trap. It has to have porous, permeable reservoir rock, and it also has to have an impermeable cap rock, such as a shale. So the reservoir rock is what holds the oil in it. And the cap rock is the stuff that keeps it from coming all the way up to the surface. If you don't have an impermeable cap rock, then the oil just goes right up to the surface and it gets destroyed by the weathering environment at the surface of the earth. So it needs to get trapped down below. The cap rock keeps the mobile oil and gas from escaping at the surface. So somewhere down below here is some type of rock that the oil can't get through. It's trapped down there. It wants to come to the surface, but it can't. And it's stored within a permeable reservoir rock, like a sandstone usually. Same thing here. And so these are common types of oil traps. This is actually common throughout the Middle East. Something called an anticline. We'll be talking about these again in a future lecture. And so this is where the rock layers are bent at one point right here in the middle. And so what happens is the oil and the gas that floats on top of the water gets pushed down. And basically you come right up to this point here and you drill a well right down into the oil. And you get all the oil out. And hopefully you get some of the gas out too, which is actually quite valuable as well. You can take advantage of faults. So here a fault has broken the layers and that's trapped the oil and gas behind it. And you could put an oil well right here, or you could put a gas well up here. In Texas and in the Gulf of Mexico, turns out big deposits of salt are of very low density and they tend to rise up almost like the way that a pluton does. And as it rises up, it breaks the rocks and it bends the rocks above it. And again, oil and gas get deposited and accumulate right next to the salt dome. And then, of course, the stratigraphic or the pinch-out trap. Remember, I was showing you those inner fingers between different layers. Sometimes you can interfinger them and you can capture some of the oil in those little fingers where things are coming together. So, sedimentary rocks. I could teach an entire class on almost every single kind of one of these rocks. And I feel like I had to rush through it to make sure I got it all covered. There's so much to be said about it. I wish that I could, do 4 or 5 lectures on it, but this is kind of a quick overview of all the different rocks. Remember, detrital rocks and the different types, mainly that you have the conglomerate, the breccia, the sandstone, and the mudstones. In this lecture, we call it both mudstone or mud rock and shale. And then don't forget your chemical and your biochemical rocks and your organic rocks as well, such as coal and oil. All right, so with that said, if you have any questions or you have any comments you want to make about this lecture, by all means send me an email or meet me on the discussion boards. Until next time, goodbye.